Hello, everyone. My name is Joshua. It's my pleasure to welcome you to this workshop on spatial market integration in R. Generally, by the time you are considering analysis of spatial market integration, we often encounter about 7 different objectives. So we shall be going through the objectives and the way to analyze each of them using R. The first objective generally is to examine price behavior, trend, and variability. In a situation, we want to use maize prices across various geopolitical zones in Nigeria. So our first objective will be to examine price behavior, trend, and variability of maize prices across geopolitical zones in Nigeria. As a reminder, the starting point is to set our working directory, go to session, set working directory, choose directory. I'm using written and OC prices folder on my desktop as my directory. So I open it. And you need to import the data, which is maize price. So this is the data set, this maize price. Let's move this up to see clearly. Maize underscore P is it here. So we click on it, import data set. As you look at the data, you have here months. So it's monthly data, and it runs from 2017 to 2026, covering all the 6 geopolitical zones. This is Southwest, South-South, Southeast, Northwest, Northeast, North Central, then the average for the country. Then we have the food consumer price index to cater for food inflation. Imports, and let's return to our code. The next thing is to load necessary packages. We need tidyverse to manipulate the data. We need duplicates to manipulate dates, T-series to perform the unit root test, URCA for our co-integration analysis, verse for causality, and various diagnostics. Then we have model summary to produce publication-ready tables, Pandoc to export to Microsoft Words. Then we need Smart ED8 for data exploration, ggplot tool, and ggpubr for plotting the graphs. Before we proceed, we need to convert the nominal prices to real prices in order to account for food inflation over time, over the analysis period. To remind us of the names, so these are the names. SW stand for the price, maize price for southwestern Nigeria. SS is for south-south, S is southeast, NW northwest, NE northeast, NC north central, NGA for the average price for the country. In order to convert to real prices, I call the real prices RP, SW, RPSS, and so on. We have to divide the maize price by the food inflation, which is the food CPI. So that's exactly what we are trying to do here. So run. So we have the real prices. For our descriptive statistics, which is um, part of our first objective. We need to extract the um, the real prices. So we use select function in our tidyverse. This is what we're trying to do here, and I call it maze underscore repeat run. And in order to obtain the descriptive statistics for the real prices, use exp start function from a smart EDA. Rand here is instructing that we need 2 decimal places. So let's run this. So here we are. So we have quite a lot of information. So you have the variable name, you have the total number of observation, number of negative, number of zeros, number of positive, negative infinite, positive infinite, number of missing, percentage of missing observations, sum, minimum, maximum. We have the mean, median, the standard deviation, the coefficient of variation, interquartile range, skewness, and kurtosis. Generally, we have to select those ones that we want to report, because in most cases, we are not reporting everything. To do the selection, I name what we want to select as DSC underscore stats. We're extracting it from this DSC stat one that we have obtained. Then we use a select function to select those one that are of interest to us. Good. So in fact, you can check the, let's see, stats. So run. So now we just have the variable name, total number of observation, median, minimum, maximum, skewness, and kurtosis. Then you can export the results as CSV. If you want to do that, you have write.csv. Then this is the name of our file. And this is the name we want it to appear in our folder. So run it. So it's already exported. So you can see it clearly here. Let's check for it. This is it. So you can just open it so that you can view. So this is it here. And it's very simple now. You can just copy it from here to Microsoft Word. All right. Let's go back to our studio. So the next thing is to plot the graphs of the real prices to show the evolution over the analysis period. To do that, we need to create a column for the date. Let us not forget we have the year column, we have the month column. So we use the two to make the date column. So we have base underscore this $date. So we have make dates. So this is making dates. That's fine. So run. So let's check. It's just a warning message, so there's no problem. We want to check the dates for the first 6 observations, so it's now in date format. And if you want to check the last 6 observations, and see, so it ends in May 2026. So we convert the data to long form. We need this so that it's going to be easy for us to plot the graph. So don't forget pivot longer. This is our data. We want to retain all these columns the way they are, year, month, and date. So we are merging all the different markets to one column and our value to another column, which is the price. So then to plot the graph, we use the ggline function in PUBR. These are our data that we have just generated. We have the X as our date, as well as the price. Then we use different colors for different markets. Yeah. So run. So this is the results. So we have the price, we have the dates, and we have different graphs for different markets. So that is that. That is exactly what we've done. So, and I think it's pretty very simple to report and discuss the graph, because what is of interest is why do we have the peak, the trough, all this kind of movement we need to actually explain. And if you look at it, there is actually a tendency for stationarity. You can see that there appears some of them actually moving together, which is a kind of starting point to test for stationarity. But we still have to proceed to test for stationarity using unit root tests. And that is our second objective. So the second objective is to test the stationarity properties of the maize prices. And in our situation, we want to use the augmented Diakey-Fuller and Philipperon test to test. As a reminder, let's check for the column names again. So these are various column names. Our interests are the prices for different zones. So we select them. That is what we call prices here. Now, in order to obtain the augmented Diakey-Fuller test for all the markets, so we call it that prices, summarize across everything. This is our ADF test, and we say dollar statistics in order to give us the statistics. So run. So you may want to check the results here. Is it here? So these are various results actually. Then we need the p-values. That's what I call the ADF underscore p. Then prices again summarize across everything. You have the ADS test, but in this case, we have the p-value, that is, give us the p-values for um, different markets. So again, you may quickly want to look at it. So in essence, these are various p-values, and of course, these p-values are higher than 0.05, which means um, at levels, the prices are non-stationary. So we try to do that also for Philipperon test. So this for Philipperon test. For Philipperon test, these are the various statistics. And for the p-values, these are the p-values. Again, the p-values clearly show that the the prices are not stationary at levels. It's very clear. So we need to produce a very clean table. This is exactly what we are trying to do here. We have our data frame. We define names for the market. We have the ADF. So then these are the ADF statistics. We have the ADF for the p-values. Then for Philipperon also. So this is, so let's produce the table. Good. So here we have the table, and you can actually export this table as CSV, as we have done before. But before we do that, let's also look at the result for force differencing. We need this force differencing because you look at um, the results for stationarity of the market prices at levels. We have seen that none of them was actually stationary. So in essence, we need to take the force difference and check again for the stationarity. So this is generating the force difference, and this is force difference. So if you look at it, you can see that the first column, as expected, are reported as any. So again, we perform the seasonality test at levels. That's exactly what we are trying to do here. The reason why we add any dot to meet is to delete this NH before producing the AGF test for the force difference prices. So run. So let's see what is doing here. But these are warning messages. It's no problem. So run. So these are various values. Then again, the p-values. So let's get the p-values. Fine. So you can now see that given these p-values, you can see that at first difference, all the market prices are stationary. So they are stationary after taking the first difference. So in essence, in terms of the order of integration, all of them are I1. So again, we repeat all those, whatever we have done also for um, PP, Filiperon. Good. Just the same thing. No, this is supposed to be PP, yeah. Good. Now we need, again, just like what we did the other time, um, we need to produce a neat table for the first differencing results. And that's exactly what we're trying to do here. Good. So run. Yeah, so this is very neat table results that we can actually export either as Excel file or to Microsoft Word. Now, we can actually pull everything together into a very neat table. To do that, I try to create a column for series level. That is for uh, test for stationarity at levels, test for stationarity at first differencing. I call it first difference here. Then my final result, I call it final underscore RS. I bind the rows, that is bind the levels result with that of first differencing. Then I select everything, select the series, the markets, and everything. So if you have done that, you have it here. So if you look at this result, you can see that we still have one minor issue before we can export it to Excel. If you look at the decimal number of decimal places, here we have about 6. So I want to round it up to something like 3. So I have the final result here. This is what we are trying to do, mutate across. That is, I'm not dealing with series and markets, so round all the others to 3 decimal places. That's what that is trying to tell us here. I have it here. So run. Good. So you now have very neat results, so that in just one table you have the result at levels, then you have the result at first differencing. So you can actually export this now to Excel as CSV file, and from there you can just copy it to your Microsoft documents. The third objective is to determine the existence and extent of long-run maize market integration across the geopolitical zones in the country. Now, as a reminder, let's get the names of what we've generated. We have seen everything here. We call it maize underscore real price, so it contains the real price, the actual price, as well as the food CPI. But our interest is just the real prices. That's what I've tried to extract again here. Let's see, maize underscore. So if you want to use this method to extract it, it's very simple. Just check where the um, check that column where the real prices begin. So you can see it starts from column 11, so 11, 12, 13, 14, 15, 16. So that is 11 to 16. So run it. Then which lag order should I use? So you use var select in order to determine that. Since we are dealing with monthly data, uh, we assume a maximum lag of 12 months. Yeah, so run it. Good. So in terms of the selection, that's our lag data selection. So now you have 12, 1, 1, 12. Always try to use this SWAS criterion. Yeah. So it always produce, in terms of law of parsimony, it always produce a kind of optimum lag order that actually um, penalize extreme. That is, you are not considering uh, extreme lag order, so it's optimized. So I'm using this criterion, which is one, actually. Please, let's see. Yeah, so in order to run the Johansson, because remember all of them are I1, so that is the essence. That's why we are considering the use of Johansson co-integration framework. Let's say it's a mixture of I1 and I0, automatically we'll be considering auto autoregressive distributed lag approach to co-integration. So I call the Jo test, that's it's in a URC package, so ca.jo function is our data. I start with trace statistics. Then now, you may wonder, why am I using k is equal to 2 when my lag data, the last selection actually suggests that I should use 1. We're using 2 because 2 is the minimum that the software can take. If you say k is equal to 1, it's not going to run. It's going to say that you need a minimum um, um, lag of 2 months. So our k is equal to 2, that is what we have used. So k is equal to 2. Then you need, in order to be sure of how many co-integrating equations that you have. So we have trace table, say data frame, hypothesis, I have R up to R equals to 5. Then the trace statistics, then assume 5% and the probability level. So let's do this and check. So you can see the results here. If you look at these results, our interest is, if you look at R is equal to 1, definitely the test statistics is 139, which is greater than the critical values. For R is equal to 1, yes, it is still greater. But if you look at R less or equal to 2, you can see clearly that the test statistics is less now. So in essence, you do not have more than 2 co-integrating uh, equations. So the first thing is, for sure, there is integration in the mixed markets in the country, and the co-integrating equation is just 2. So since you have a sort of co-integration that is a long-run relationship among the markets across geopolitical zones in the country, mixed market prices, then you need to estimate the vector error correction model so as to examine the short-run as well as long-run price adjustment mechanism. So to do that, we estimate the PECM here, which is what we have here. Yeah. Then you have the summary of the models as VCM $RLM. I call it the coefficient tab 1 because I will use it to create the table for the results. So in order to see all the results for different markets, I use model summary package. So model summary list, Southwest is this RPSW model, and so on and so forth. These are for the 6 different models. And I say, okay, add star for significant coefficients. So you've done it correctly. Let's run it. So these are various results. But our interest actually is this ECT. This ECT. Because it actually measures adjustment towards long-run equilibrium. Yeah. And you can see there is just one market that is actually showing adjustments towards long-run equilibrium. All the others, though, are showing a good sign, but they are insignificant. Then the next objective is objective 5. Since we have co-integration among the markets, we are saying that at least a market is showing strong adjustments towards long-run equilibrium. Then we need to estimate the direction of price transmission and mixed market leadership across different zones. So this is exactly what we are trying to do here. In this case, before you can do it, you have to delete the earnings in our price differences. So I call it price underscore div2. So run. So in essence, I need to find out whether each of the various markets Granger costs that is predicts what is happening in other markets. So in essence, I run it, I use each one. So let's run that of let's run everything because we place it in table. So this is then I arrange them in a table. So I'll show us. So I arrange everything in the table. So this is the Granger table. So let's run the Granger table. Fine. So this is the Granger table. And if you look at these p values, all of them are actually greater than 0.05, which means in terms of Granger causality, none of them actually Granger cause um, what is happening in other markets. So they do not predict what is happening in other. That is what we are trying to say is that the previous year price of any market um, do not predict what is happening in other markets based on what we have here. But you know, there are two types of causality. This is one. The other one is called instantaneous causality, and we are still going to carry that one out. What that one is telling us is that is there any shock in the market? And if there is any shock in the market, how does it affect uh, the other markets? So that is exactly what that one is trying to solve. And in terms of instantaneous causality, you know, the other one is actually looking at the previous price as affecting what is going on now in other. But in this case, we are dealing with the current. So is there any shock driving what is going on in the market and what is the influence on other market? That is exactly what we're trying to look at here. And we all know that, particularly in Nigeria, there are quite a lot of market shocks. Uh, Currently, for instance, we have um, rising cost of fuel. We have political crisis. We have issue of bandits and all sorts of things affecting market prices and so on. So such shocks is what we are trying to look at when we are discussing instantaneous um, causality. So in terms of instantaneous, this is what we call IC, whatever. Then we arrange everything in table, just like what we've done with the Granger. So this is the results. So if you look at this result, you can see that in terms of instantaneous causality, um, all the markets instantaneously predict what is happening in other markets. So we can see that shocks is very, very more important to this kind of study. And to me, it's always good to report both of them and discuss the results. Then you can export this to Microsoft Word. Then objective 6 is to analyze the response of that base price to market shocks. That is using import response function. So this is our import response function model. IRF function is this. So in this case, we want to check whether you want to check the response of the North Central maize market to the yield of shock in southwestern Nigeria uh, mixed markets. So we are forecasting for 12 months. So this is it, then let's run it. Yeah. So then the last objective is to estimate the adequacy and reliability of the estimated vector error correction model. So in terms of necessary diagnostic tests, we have the serial correlation test, we have normality tests, then we have stability tests. Then we can test for heteroscedasticity using patch test and so on. But let us just work on these three, for instance. So run it. So our interest is just check for this p-value. So in this case now, the um, the test for serial correlation is showing that value is 0.02 is confirming presence of serial correlation. Normality, so the normality assumption also is validated. Then in terms of Kusum, of different equations, that is what we have here. You can see some kind of explosion here, because not all of them actually fall on the line, and it differs from market to market. So thank you very much. This is just, I think this is just exactly what we've done. I believe you have to take your time to go through them and to read more about the interpretation and all sorts of things. So thank you. God bless you. Until we meet again.